Hi, good to see you again. Today I will present to you the challenge of decarbonizing heat in the built environment. In today's lecture, we will define what it means to decarbonize heat and how we can take steps to do so. We will also identify some real-world examples that have already taken steps towards decarbonizing heat. First, we need to understand the carbon impact of us, people. In the EU project called Citizen, the carbon footprint of households in various European cities was analyzed. Here we see the figures of Amsterdam, the Netherlands. In this table, we can see that a considerable part of the energy use is related to heat, which is what we already learned in my earlier lecture. As you can see on the bottom right corner, the overall carbon impact of a Dutch household is 8.5 tonnes per annum. Is that a lot or not? We have no good understanding of carbon emissions yet, which is why I prefer to translate it to the forest area required to sequester these emissions. And here you see the outcome. The forest required to compensate for the emissions of a Dutch household is approximately 1 hectare, equivalent to 1.7 football pitches. This is based on research by carbon accounting expert Riccardo Puccelli. Mind, this is necessary for the household's energy, car mobility, water use and waste production. Food, equipment and stuff, as well as flights and boat trips are not included and probably comprise 1.5 times more. So you may actually assume 4 football pitches of forest for all emissions together. That's quite some space we need around every single house. With the current population density, this is impossible, which is why we must decarbonize our daily life, including heat. What is decarbonizing heat? It is excluding all energy sources that emit greenhouse gases, the typical fossil fuels, coal, mineral oil and natural gas. Burning biomass also emits carbon, but since this carbon was once stored in the tree or other plant, the EU considers biomass as a carbon-neutral energy source. Burning trees, however, releases the carbon stored during the growth of trees. So, burning wood can only be carbon neutral if an equal amount of carbon is sequestered while burning wood. And that is difficult. A furnace incinerates a tree trunk faster than a tree or comparable wood matter can grow. No wonder this is controversial, regardless of all other functions that wood can have before being incinerated. Using biomass or biofuels from residual organic matter is less of a controversial topic. This material could otherwise be rotting away and releasing greenhouse gases. Better to use them functionally then. Now we understand what decarbonization means, we can have a look at the design of decarbonized buildings. Therefore, we take this approach as the basis. Before we draw or engineer anything, we need to understand the local circumstances, such as the climate, underground, surroundings, building brief, etc. The next step is to reduce the energy demand by design measures. Step 2 is about optimally reusing residual flows, such as waste heat. The last step is the production of renewable energy to supply the remaining demand. So, the design process always starts with reducing the demand, and there are a lot of possibilities to do so. Here you see a list of architectural measures on the left and technical measures on the right. Equipment you need anyway can better be energy efficient. In case of an existing building, the highlighted blue measures can still be taken, quite a lot still. In yellow you find the measures that influence the demand for heat, hence which can contribute to the decarbonization of heat. Now let's see how we can decarbonize the demand for heat in cities. These are images that you already saw in my previous lecture. They indicate the energy labels and gas use in the city of Amsterdam. Zooming into a historic city, which uses a lot of gas for its heating purposes, let's see what we can establish there. One advantage of an energetically inefficient area is that a lot of progress can be achieved. For instance, by saving energy through post-installation roofs, facades and ground floors, and through replacement of poorly insulating glass. After saving the heat demand, a switch might be possible to heat pumps, which are more efficient than gas-fired or electric boilers. Step 2, reusing residual energy, is even more interesting when looking at an urban context. When we acknowledge that different urban functions have different energy patterns, it seems more logical to exchange heat than to make each building self-sufficient. So, the waste heat of cooling processes of some urban functions can supply functions that require heat, creating an optimal ecosystem of energy exchange, possibly with interseasonal storage in between. One clear example is a supermarket, which is cooling all year round, hence releasing waste heat continuously. If we capture that waste heat, we can use it to heat apartments around the supermarket. This is what my graduate student Nick ten Kaat did. He designed a combined energy system of a supermarket and the urban block around it. According to his calculations, his system would save 60% of carbon emissions, not even including renovation of the residential part. If solving it within the same urban block is not possible, a low-temperature heat and cold network can transport heat from one spot to the other. That way we create a sort of internet of heat, with urban functions that upload their waste heat and others who download it when needed. Apart from supermarkets, heat sources can be cooling processes of department stores, waste heat from underground tubes, geothermal and aquathermal energy. Therefore, it is recommended to chart the energy potentials of the respective area. Here we see the analysis of this part of Amsterdam. Next to waste heat and heat from the sun, due to the abundant availability of canals, aquathermal energy proves to be most promising. Aquathermal energy has a lot of advantages. Firstly, when you take heat from open water, its temperature will decrease. This will improve the water quality, which at present is much warmer than it used to be, due to climate change and due to discharge of heat into the water. So, making it cooler will reduce the algae and bacteria now flourishing in the warm, nutrient-rich water. This cooling of water will also help to cool the city in summer, provided that also in summertime heat is taken from the water and then stored underground for usage in wintertime. But the nicest advantage of using aquathermal heat is that also in wintertime the water will be cooler, creating a greater probability of ice formation. Ice skating is one of the most loved activities in the Netherlands, so this sustainable interventions enables a cultural and sportive activity that otherwise would hardly be possible anymore under climate change. So, apart from saving energy and costs, decarbonizing heat can provide many advantages to the built environment and to people. Therefore, I recommend to continue and to follow up with the next lecture. Good luck!